When we hear the term AI, most of us probably think of ChatGPT and similar applications that have emerged in recent years. The reason these applications have seen such a boom only recently, aside from significant work done by brilliant scientists, is that they require an enormous amount of data and computational power which we only recently had available.
But AI has actually been around for over 70 years, and in that time, it has made its way into almost every aspect of our lives. From navigational systems that find the best way to avoid traffic jam, or drones that can return home and land safely even if they lose signal, and even to robotic vacuum cleaners that keep your floors spotless. In this video, we'll explore how to create an AI for a robotic vacuum cleaner. In the first part of the video, we'll briefly explore a few key ideas and principles that form the foundation of AI. Then, in the second part, we'll get into designing AI for our robotic vacuum cleaner and tackle the challenges that come up along the way.
First, we'll figure out what we want our robot to do and how we'll measure its success. Next, we'll think about how to use math to describe the environment our robot will be cleaning. After that, we'll teach the robot how to move around in this environment. We'll then use that knowledge to help it clean as efficiently as possible. And finally, in the last part of the video, we'll see how well our robot performs and think about what we could do to improve it. Now that we've got a clear plan, let's jump in.
Let's start by exploring how scientists approach solving problems with AI and how they name the different elements involved. In this video, we'll use the example of a robotic vacuum cleaner that needs to clean a room to illustrate these concepts. The vacuum cleaner moves around a room filled with various obstacles, like furniture, for example. We will call this room and the obstacles the environment. In this environment, we have our robotic vacuum cleaner, which, in the context of AI, we often refer to as the agent.
Our agent has wheels that it uses to move around and turn. These are called actuators. It also has sensors that help it perceive its surroundings, like infrared sensors that tell it how far away it is from obstacles. The actuators and sensors together make up what we call the agent's architecture. Actuators aren't just wheels. They can be things like robotic arms or even speakers. Basically, anything the agent can use to interact with the environment. Similarly, sensors can include cameras or even something a bit unexpected, like text input for ChatGPT. Now think about the architecture of us humans. What sensors do we use to perceive the world? And what actuators do we have to change it? Let us know your thoughts in the comments.
So far, we have described the environment, which in our case is the room, and the agent, whose architecture we have just covered. But for the agent to actually clean the room, we need one more crucial thing: a brain. The agent's brain works almost like our brains do. It processes information from the sensors, like distance to obstacles. Based on this information, the agent might decide it's time to start braking to avoid hitting a wall, for example. It then sends this instruction to its actuators as a brake command. In practice, we call this brain the agent program.
When you're solving a problem with AI, the first step is to define the environment where the problem takes place. Next, you need to figure out your agent's architecture. After that, you design the agent program that will control your robot. The third part is often the hardest, and it takes the most time. But even if your job is just to design the agent program, you can't ignore the first two parts. To create a good agent program, you really need to understand both the environment and the architecture of your agent. Now we're going to break the rules a bit and try to design an agent program for cleaning without diving deep into the agent's architecture or the environment it will work in.
Our inspiration for this program will come from nature. Most animals, including us, have deeply ingrained reflexive reactions to various stimuli. For instance, when you touch boiling water, you instinctively pull your hand away without even thinking about it.
We can apply this idea of reflexive reactions to our vacuum cleaner. To do this, we'll need the actuators to allow the robot to turn and move forward. The sensors should notify us whenever the robot bumps into a wall. The agent program will work like this. When we turn on the robot, it will move straight ahead. Every time it hits a wall, it will turn by a random angle and then continue moving forward. If we let this robot run long enough, it will eventually clean the entire room.
We might be tempted to say we have found a solution and just move on. But is it really the best solution? Not by a long shot. Intuitively, we know it's not perfect. To accurately assess how good our program is, we need to think about how the cleaning progresses and what we actually want to achieve. We'd probably want the vacuum cleaner to clean as much of the area as possible, while taking the shortest amount of time.
It might seem obvious what do you want from a cleaning robot, but to design the best cleaning robot, we need to quantify it. Logically, our goal is for the agent to clean the entire room, but the reality is this isn't always possible. From a geometric perspective, our agent can only clean a circular area around itself, which means it might struggle with cleaning spots like corners. Today's robotic vacuum cleaners often have rotating brushes that help them clean the spots they wouldn't reach otherwise. But there can still be situations where even this isn't enough. So practically speaking, we won't demand that the robot will clean the entire room, just a certain portion of it. For this video, we'll set the target at 90%. When we apply this threshold to these three cleanings, we find that the first and third meet the requirement, while the second doesn't. Whether the robot cleans 93% like in the first case or almost 91% like in the third isn't important to us. Because there's another important difference between these three cleanings, and that is the time it took to finish.
So the question is, how do we calculate the time it took for the robot to complete this task? To do this, we need to know two things. First, how fast the robot moves, and second, how fast it turns. With this information, we can calculate that the first cleaning took 3,517 seconds, the second 724 seconds, and the third cleaning took 1,077 seconds. We can figure this out by calculating how long each instruction took and summing those times. But more interesting than the calculation itself is what these numbers tell us. It's pretty clear that cleaning time of 724 seconds or 1077 seconds is better for us than 3517 seconds. So we can compare agents based on cleaning time and the percentage of the room they cleaned. But often it's very useful to have a single number that tells us which option is better.
For this, AI researchers use a function called performance measure. You give it information about how the agent acted in particular situation, and it gives you a single number that reflects how well the agent performed. The higher the number, the better the agent did. Let's think about how we could design such a function for our problem. We definitely want this function to be 0 if the robot cleans less than 90%, because if it cleans less, it hasn't completed its task. At the same time, we want it to have a higher value when the robot cleans faster. We will create a function that takes the percentage of the area cleaned and the time it took to clean as an input and define it as a piecewise function. If the robot cleans less than 90% of the area, the function will output 0. On the other hand, if the robot cleans at least 90% of the area, the function will output 1 over t, where t stands for time. The key here is that 1 over t is a decreasing, non-negative function on positive real numbers. So, the longer it takes the robot to clean, the lower its score will be. Now think whether this function might break down in some situations from a mathematical perspective. If you find any issues, try to solve them and share your thoughts in the comments. Also, if you're familiar with the step function, you could think about a way to rewrite our function without needing to separate it into different cases.
Now, let's see how this function evaluates our 3 cleaning attempts. In the first case, the score is 1 over 3,517. In the second case, it's 0 because the robot cleaned less than 90% of the area. And in the third case, it's 1/1077. This allows us to rank the cleaning attempts from worst to best. The second attempt is the worst, the first is better, and the third is the best. This concept is fundamental to the field of artificial intelligence. One of the main goals of AI researchers is to develop agent programs that perform best according to some performance measure function.
This is a really challenging task that requires deep knowledge from various fields. When designing a program like this for a robotic vacuum cleaner, you have to consider all the complexities of the real world. The robot doesn't have anyone to tell it exactly where it is, so it has to figure out that using its sensors. But sensor readings can be thrown off by something as small as a speck of dust, making it read a distance of 1 meter when it's actually free. The same goes for its actuators. The vacuum cleaner never moves exactly as intended. For example, its wheels might slip. Plus, someone could step in its path or even pick it up and put it somewhere else. All these issues can be solved, but the solutions rely on some pretty advanced math. To simplify these problems and make them easier to handle, we'll create a mathematical model that will help us show you the key principles of artificial intelligence. The idea behind mathematical models is to describe a problem as simply as possible. For a rocket scientist, this might mean describing a satellite's trajectory with a simple curve. For a chemist, it might mean describing a reaction using a function. For us, it's about describing the process of cleaning a room with a robotic vacuum cleaner using mathematical tools we'll show you in the rest of the video.
To keep things simple, we'll describe the world where the vacuum operates in 2D. Of course, we live in a 3D world, but for our example, 3D would bring too many complications, while the core idea of the algorithm would stay the same. We'll do this by picking several points on a plane and connecting them to form a polygon. The points we use to build the polygon are called vertices, and the segments that make up its boundary are called edges. All the points inside the polygon and on its boundary will represent the floor area of our room. But in real rooms, there are often obstacles on the floor, like furniture. We can also represent these obstacles using polygons. For each obstacle on the floor, we'll create a polygon that marks the area where the robot can go.
Robotic vacuum cleaners are usually shaped like a cylinder, but since we're working in 2D space, we'll describe it as a circle. From a mathematical perspective, a circle is defined by two parameters, the center point P and the radius r. A circle with a center point P and radius r is the set of points that are at most r units away from P. This effectively describes the vacuum's position and the area it can clean at that position. Now, let's look at how we can describe its orientation.
One way to do this is by using a direction vector that specifies the direction the vacuum is facing. For example, vector 1, 0 describes that the vacuum is facing to the right in a 2D space, while the vector -1, 0 describes that the vacuum is facing left. But we need a simple way to describe all possible orientations, not just those where we can easily deduce the directional vector. This is where the unit circle comes in handy. The unit circle is a circle centered at the origin of the Cartesian coordinate system with a radius of 1. This circle has several interesting properties that will be very useful to us. Points on the circle represent all possible normalized direction vectors in 2D space. A normalized vector is a vector with the length of 1. So, any orientation of our robot can be described by a point on the unit circle. The unit circle is also closely related to trigonometric functions. They allow us to elegantly describe all possible orientations of our robot. If we choose a point on the unit circle and label its coordinates x and y and its angle alpha, then x equals cosine of alpha and y equals sine of alpha. This means that we don't need to store the direction vector itself. We can just store the angle, a value like pi/3 for example, which is an angle in radians corresponding to 60 degrees, and it represents this directional vector. So far, we have described how we'll represent the room our agent will be cleaning, the obstacles it might encounter, the agent's position and area, and its orientation in space. But we are still missing something. We need actuators to move the agent around the environment and sensors to perceive the environment.
Let's first look at how to make the agent move. A real vacuum has wheels that allow it to rotate and move forward. We'll describe this in our model using mathematical operations. Let's start by looking at how our robot could move forward by, say, 2 units. For this, we'll need the directional vector. Movement in the Euclidean space can be described as vector addition. We simply add twice the directional vector to our agent's position, which describes a shift of 2 units forward in the direction it's facing. But rotating our robot is a bit more interesting. Let's go back to the unit circle. If we take a point on the unit circle and add the angle beta to it, we get a new point that corresponds to the rotation of this directional vector by angle beta counterclockwise. So we don't need to come up with any complicated rotation procedure. We just need to add or subtract values to our angles depending on which way we want the robot to turn.
Finally, let's describe the sensors. We could create a complex mathematical model that includes all the real-world complications, but we are not going to do that. Our goal is to show you the basic principles of AI, and a sophisticated sensor model would just complicate things. Instead of sensors, we'll make the robot omniscient, giving it complete information about the environment model. This means its sensors will provide an exact description of the room it's in, along with precise information about its position and orientation. Now that we have broken down how our environment works and the architecture of our agent, we can finally start solving our problem. Imagine you're in this room and want to get from point A to point B. For us humans, it's pretty simple. We would intuitively walk along a path that might look something like this curve. But for a robot, it's not that easy. It might try to face the target point and move straight ahead, but then it would hit a wall. The main problem is that there are infinitely many different paths from point A to point B. Computers, however, can only work with a finite number of options, so we need to limit the number of possible decisions for the robot. We can do this by doing discretization of the environment. What does it mean? It means breaking the environment down into a finite number of clearly defined points, which we will call vertices. We'll then restrict the robot to only travel to these points, which will simplify its decision-making and help us create an algorithm that finds a path from point A to point B. We'll figure out how to create such a path in the upcoming chapters. But first, we need to decide how to divide the room into these vertices.
Our goal is for the robot to clean more than 90% of the room. So we need to pick a set of vertices in such a way that visiting them all will cover at least 90% of the area that needs to be cleaned. You might think that it is a good idea to use a lot of vertices to cover the entire room, but there's a catch. The more points we include, the longer it will take the algorithm to figure out the best cleaning route. Plus, many of these points won't be even necessary. So choosing too many points isn't the best idea, and we need to come up with a smarter solution.
The strategy we'll use is inspired by an old math problem. Imagine you are asked to place circles of the same size on a flat surface so that they cover as much space as possible without overlapping. This problem is called circle packing, and the solution is surprisingly simple. If you divide the space into a hexagonal grid and place a circle at each vertex and at center of each hexagon, you will cover about 91% of the area. But for our purposes, we will go with an easier strategy. We'll use a square grid, shrinking the squares so the circles just touch at the center of each square. This ensures that when the robot visits all the vertices, there won't be any spots left uncleaned. Here is a quick geometry question for you. If each circle has a radius of r and all 4 circles intersect at the center of this square with sides of length d, what is the value of d? Share your answers in the comments.
Using the value of d, we can easily generate a set of vertices by first creating a vertex at some starting position, then adding another vertex shifted by d to the right. We repeat this several times. Then we add a whole row of vertices and shift it up by d. And again, we will repeat this process several times. This strategy allows us to generate a set of vertices that nicely fills a rectangle. But we want to fill our room, which isn't a rectangle but a polygon. So we'll need to remove some of those vertices that we have generated.
Notice that any points with an x-coordinate smaller than this line definitely don't lie inside our polygon, so we can safely remove them. Similarly, we can remove points with an y-coordinate that is too small, an x-coordinate that is too large, and y-coordinate that is too large. By doing this, we have essentially wrapped our polygon in a rectangle and discarded all points outside of it. But we still have some vertices that clearly don't lie inside the polygon. Let's look at an algorithm that can handle these points.
Let's say we have a polygon and 3 different points. Point A lies outside of the polygon, point B lies inside, and point C lies on its boundary. We can test whether point C lies on the boundary of the polygon using high school geometry. For points A and B, the situation is more interesting. We'll assign them directional vector and use them to construct rays. Notice that the number of intersections between ray RA and the polygon is even, while for ray RB it is odd. However, this rule has 2 exceptions. The first is when the directional vector of a ray is parallel to one of the polygon's edges, which could cause an infinite number of intersections. The second exception occurs when a ray intersects one of the polygon's vertices in this way. In such a case, the number of intersections for ray RA would be odd, and for ray RB it would be even. Think about how you could algorithmically choose the directional vector of the rays to avoid both of these exceptions. We'll give you a hint. There are only a finite number of directional vectors that can cause these exceptions. Using this, we can design an algorithm that determines whether a given point is part of a polygon or not. First, we test if the point lies on the polygon's boundary. If it does, we know it is part of the polygon. If not, we construct an array using a directional vector that avoids all of the mentioned complications and check whether the number of intersections is even or odd. If the number is odd, the point is inside the polygon. If even, the point is outside the polygon. Now, if we take our set of vertices and the polygon representing the room, we can easily determine for each point whether it is part of the polygon. If it is, we keep the point, otherwise we throw it away. But our room also has obstacles that the robot can't pass through. So it doesn't make sense to keep vertices inside them. We can use our algorithm again, but this time we discard a point if it belongs to a polygon representing an obstacle, and we keep it otherwise.
But there is still one problem. Some points are so close to the edges of our room or obstacles that the robot still can't reach them. We'll need to remove them as well. For simplicity, let's consider a line segment and 2 vertices, A and B. If we can calculate how far points A and B are from the line segment, it's clear that point A needs to be removed because it's closer to the line segment than the robot's radius, while point B can be kept. Try designing an algorithm that calculates the distance from a point to a line segment and then share it in the comments. It might help you to use a line that passes through the line segment. We have designed an algorithm like that, and we'll use it to remove all vertices that are dangerously close to any obstacles or the room's boundary.
Now imagine the robot is at a specific vertex. Which other vertices can it reach by simply turning around and moving forward? there are quite a few such vertices. You might think it is a good idea to allow the robot to travel to any of these vertices. But there's a catch. If we do that, the robot would have too many options at each vertex, which would make it really slow to decide. Let's focus just on two specific vertices. We can construct a path that gradually hops from vertex to vertex until the robot eventually reaches its destination. So we don't need to teach the robot how to travel to every possible vertex it can reach without hitting a wall. It is enough to show it how to move to neighboring vertices.
This brings up a question. How do we decide which vertices are considered neighbors? One option is to treat the 8 surrounding vertices as neighbors. This way, we can create a grid that outlines the possible connections between vertices. The robot's movement between points would look something like this. Another option is to connect vertices only horizontally and vertically. This gives us a simpler grid and movement pattern for the robot. A third option is to connect vertices along diagonal axes, which creates yet another grid and a set of paths for the robot. Each option has its pros and cons. In practice, the second option tends to be the easiest to work with, so we'll stick with it for the rest of the video. We'll treat the grid as a map that helps the robot navigate the environment. Take a moment to think about the advantages and disadvantages of each option. Is any of them the best choice in every situation? Let us know your thoughts in the comments.
Before we teach the robot how to navigate the environment, let's ask ourselves, does our map actually make sense? Back when people didn't use smart maps, you might have planned a driving route, only to find out halfway through that the road was closed. Couldn't something similar happen to our robot if it planned its route using this map? In most places, the map seems fine, but there's one spot where this problem might occur. If the robot is placed at vertex A and we want it to move to neighboring vertex B, it would hit an obstacle. To prevent this and give our robot a map that actually works, we'll need to remove such edges from the map. Notice that if any point on an edge would cause a collision with an obstacle, the distance between that point and the obstacle is less than the robot's radius. So the question is, how do we determine if there is a point on the edge that's closer to the obstacle than the robot's radius? If we could calculate the distance from edge to every edge of the obstacles and the room, we would simply take the minimum of these distances to find the closest edge where the problem might occur. So let's look at how to calculate the distance between two edges. In other words, we want to find the distance between two line segments. Two line segments in a plane either don't intersect at all, intersect at one point, or intersect infinitely many times. If they intersect at least once, their distance is 0 because they share a point. If the segments don't intersect, calculating the distance is more interesting. We calculate 4 distances. Distance from point A to segment CD, the distance from point B to segment CD, the distance from point C to segment AB, and the distance from point D to segment AB. The smallest of these 4 distances is the distance between segment AB and segment CD. Pause for a while and try to think about why this algorithm works. Returning to our original problem, we simply calculate the distance from the edge the robot is traveling on to all the edges that make up the room or any obstacles. If any of these distances is less than the robot's radius, like in this example, we remove the edge. Of course, we'll have to do this for all the edges. This finally gives us a map that will work.
Before we show the robot how to navigate this map, there is a little secret we need to share with you. Our map actually hides a very interesting mathematical structure. We call it a graph. You might be thinking that this can't be a graph, since graphs look like this, not like a grid. In reality, our grid is what mathematicians call a graph, while the thing that you know from high school is called a graph of a function. Graphs consist of vertices and edges. The vertices represent some objects, in our case, points in a two-dimensional space. The edges represent relationships between these objects. In our case, we connect two vertices with an edge if the robot can travel between them along a straight line. Graphs have fascinated mathematicians for a long time, and there is even a whole field of mathematics dedicated to them: graph theory. But with the advent of computers, another group of people became interested in graphs: computer scientists. They have used graphs to create a huge number of groundbreaking technologies, like recommendation systems on platforms like YouTube, search engines, and even navigation systems. In this video, we'll show you how graphs are used in navigation.
When we use navigation, the main goal is usually to find a path from point A to point B. But what exactly do we mean by a path? In our case, a path is a sequence of vertices that our robot can follow to move from vertex A to vertex B. The key point is that each pair of consecutive vertices must be connected by an edge. But this isn't just any path, it's a path in a graph. Mathematicians have been studying these paths for a long time and have developed a lot of related concepts. One important concept is the length of a path. We define length simply as the number of edges the robot must cross while following the path. For example, path P1 has a length of exactly 64.
If we need to guide a robot from point A to point B, there are many possible paths we could choose. But some paths are clearly better than others. Besides path P1, the robot could take path P2, which is 56 edges long, or path P3, which is 50 edges long. If we want the robot to get there as quickly as possible, it makes sense to choose path P3 because it's the shortest of the three. But why not pause the video and see if you can find a path that is even shorter than P3? Here is a hint. Such a path exists, and it's, for instance, the path P4, which is actually the shortest possible path between these vertices. The shortest path, as the name suggests, is the one with smallest possible length. There might be several shortest paths, but finding just one is good enough for our purposes. So let's see how we can find such a path using an algorithm.
We'll use an algorithm that calculates the distance from any vertex in the graph to a starting vertex. The distance between two vertices is simply the length of the shortest path connecting them. The distance from starting vertex to itself is of course 0, because there's no need to cross any edges to reach it. To reach the vertices directly connected to the starting point, we cross a single edge, so their distance is 1. Next, we'll go through each vertex with a distance of 1 and assign a distance of 2 to all its neighbors that haven't been assigned a distance yet. Since we can reach them by crossing one edge from a vertex with distance 1. We'll keep repeating this process until there are no more reachable vertices without assigned distance. The end result will be a structure that lets us easily identify the shortest path from any point in our graph back to the starting vertex. We do this by starting at a vertex where we want to end up, and then follow the path of decreasing distance values. With each step, the distance to our target vertex decreases by 1 until we eventually get there. The sequence of vertices we pass through will make up our path.
Now, we've got a sequence of 47 points in a 2D space. The next step is to get our robot moving along the planned path. However, to the robot, this path is just a sequence of vertices, and it doesn't understand it at all, because he only understands simple instructions like move forward or turn. So let's play translator and convert this path into instructions that the robot can actually follow.
First, let's figure out how to tell the robot to move from point A to point B when we know there are no obstacles between the points and the robot is already facing the right direction. We need to tell the robot how far to move. To do that, we need to calculate the distance between points A and B. In high school geometry, you probably learned that the distance between 2 points in 2D space can be calculated using the Pythagorean theorem. How long is the side A? That's simply the difference of the x coordinates taken as an absolute value. And the length of the side B is the absolute value of the differences of the y coordinates. Then it's just a matter of applying the good old Pythagorean theorem.
So, what if the robot isn't facing the right direction? We need to rotate the robot by the angle between its current direction vector and the vector pointing from point A to point B. We'll do this using the dot product of two vectors. You might remember from high school that the dot product of two vectors is closely related to the angle between them. You have probably worked with a formula that looked something like this. And this is exactly the formula that we will use now. By applying the arccosine function to the result, we get the angle alpha by which we need to turn the robot. In this particular case, we can tell to the robot to rotate by an angle alpha and then move forward. But what if the robot's original orientation was O' instead of O? The angle between those vectors would still be the same, but in this situation, we would need to turn the robot by angle negative alpha instead of alpha. Try coming up with an algorithm that can determine whether to rotate the robot by alpha or negative alpha, and share your solution in the comments. You can use your knowledge of trigonometry, or if you are more advanced, even determinants.
With this algorithm in place, we can now convert the entire path into instructions. We'll do this by going through each vertex of the path one by one. At the first vertex, we check if the robot is oriented correctly. Because it isn't, we'll tell it to rotate by 61.29 degrees. Then we'll tell it to move forward by 0.21 meters. This brings us to the next vertex, where we repeat the process. By following this method through the entire path, we get a sequence of instructions that the robot can understand. You might be thinking now that figuring out the rotation angle was unnecessary, because our robot only moves up, down, left and right. But that's not entirely true. Now we can convert paths into instructions even on non-square grids, which can be very useful.
To fully solve our task, we are missing one final piece. We need to find a path for the robot that will allow it to clean the entire room. So we're gonna try to find a path that passes through every vertex in our graph at least once. Ideally, we would want to find the shortest path that does this, but that's a bit too complex for this video. Instead, we'll show you a simple algorithm that will find a path that covers all the vertices, but it won't guarantee that this path is the shortest possible one.
The algorithm works by dividing the set of vertices into visited and unvisited. Initially, all vertices are unvisited, which we'll mark with a red color. We'll pick one of these vertices as our starting point and mark it as visited. Next, we'll calculate the distance from this vertex to all other unvisited vertices, and we'll mark the nearest unvisited vertices in pink. From the pink vertices, we'll choose one and move towards it using the shortest path. Once we reach it, we'll mark it as visited and repeat the process. As you can see, at each step we typically have several different vertices to choose from. Do you think this choice affects the length of the resulting path or the time it takes to complete the route? Don't forget that turning the robot also takes time. The algorithm continues like this until there are no unvisited vertices left that can be reached. Once the algorithm has visited all such vertices, it stops. The output of the algorithm is the sequence of vertices it visited during its run. This sequence forms a path that passes through all the vertices in our graph. An interesting feature of this algorithm is that it behaves greedily. In each step, it picks the option that seems best at the moment. In this case, moving to the nearest unvisited vertex. While this algorithm will find the path that covers all the vertices in our graph and will usually be fairly short, it doesn't guarantee that this path will be the shortest one. However, this path will definitely be good enough for our purposes.
Let's finally take a look at what happens when we convert this path into instructions and give them to the robot. As you can see, our solution works. The robot cleaned over 91% of the room, which meets our success threshold. Plus, it managed to do this in just 1080 seconds. A robot that uses reflexive reactions had to run for almost an hour. So it was definitely worth the effort to come up with a more sophisticated algorithm, as our robot now cleans more than 3 times faster.
Cutting down the cleaning time any further wouldn't make much of a difference, since our robot is already pretty efficient and doesn't waste much time. But what could be improved is the area our robot cleans. We set our threshold at 90%, but we could easily raise that to something like 96. In that case though, the algorithm we designed wouldn't be sufficient, as our robot cleans only 91.08% of the room. Do you have any ideas on how we could modify the performance measure function so that it still enforces the 90% success threshold, but also gives better ratings to robots that clean say 96 compared to those that clean 91%, assuming that take the same amount of time?
If we want to improve the rating given by such a function, we'd certainly focus on increasing the percentage of the room that's cleaned. One option might be to make the grid smaller, which would increase the area the robot covers, but this would also slow down the cleaning process quite significantly, so it wouldn't really improve the rating. A better approach might be to add extra instructions to our existing path, telling the robot to circle around the edges of the room and obstacles. This would allow the robot to clean most of the spots it missed before without slowing down the cleaning too much. Another option could be to design the grid so that more vertices are placed around the walls and obstacles than in the rest of the room.
What do you think? How could we make our algorithms even better? We would love to hear your ideas, so drop them in the comments. That's all for today's video. Thank you for watching.